Welcome everyone. My name is Mattia Sabatelli and I will be the lecturer for today. And together we will be covering the topic of reinforcement learning. So this is a brief outline of today's presentation. I have divided it into three main parts. First of all, I will briefly introduce myself, and then we will dive into the world of reinforcement learning. We will see three different methods. So usually when it comes to reinforcement learning, we divide the family of algorithms that tackle reinforcement learning problems into three main families. These families are value-based methods, policy-based methods, and model-based methods. Probably each of these methods would deserve one lecture on its own, but the goal of today's lecture is to just give you an introduction about what the general idea and the general intuition behind these three family of techniques is. And then of course I would like to mention something about what these days comes with the name of deep reinforcement learning, which is the combination between classical reinforcement learning algorithms and neural networks, therefore deep learning. So before we start, something about myself. As you might probably guess from my accent or my name, I'm Italian. I studied in the very north of Italy at the University of Trento. This is where I got my bachelor's degree between 2010 and 2013. After that, I have decided to come to Holland, and that's where I did my master's. I did my master's in artificial intelligence here at the University of Groningen. This took me a little bit longer than expected, so between 2014 and 2017. And after my master's, I moved to the University of Liège, or the University of Leuc. That's in the French part of Belgium. That's where I got my PhD at the Department of Electrical Engineering and Computer Science. And right before finishing my PhD, I came back to Holland. I first worked a little bit as a lecturer at the University of Groningen, and once I obtained my PhD, then I became assistant professor, and right now I'm assistant professor in reinforcement learning at the Bernoulli Institute, which is part of the Faculty of Science and Engineering. My excuses. And at the Faculty of Science and Engineering at the University of Groningen, we have different groups, of course, especially when it comes to people who do AI research. So we have a cognitive modeling group, we have a group which deals mostly with the logics, and then we have the autonomous perceptive systems group, which is the group I'm from, and that's where we focus mostly on all forms of machine learning, ranging from supervised learning to reinforcement learning, which is of course the topic of today's lecture. So if you've heard of machine learning before, and I think you did based on the previous lectures that we're giving as part of this school, you should know that we can typically divide it into three main parts. So machine learning is divided in three main branches: supervised, unsupervised, and reinforcement learning. Of course, there's other subcategories that one can add to this list, but the community seems to agree that indeed these are the three main ways of doing machine learning. If we would have to summarize them, the goal of supervised learning is that of learning from labeled data. So we have access to a large data set that typically consists of input-output pairs, x and y's, and these input pairs can come in the form of feature vectors or images, and then the y, basically what we are trying to train the machine learning model on, depends whether we are dealing with what is called a classification problem. Then the y usually comes in the form of a categorical variable. Basically, I don't know, you have a big bunch of images and you want to classify cats and dogs, for example. But it's also possible that the y we're trying to predict comes in the form of a numerical value, and in this case we are dealing with a regression problem. But overall, the goal of a supervised learning algorithm is to learn a mapping from x to y, where x is our input data and y is what we're trying to predict. Now in unsupervised learning, what happens is that we do not have access to this labeled data. So usually we still have a bunch of data we can learn from, so our X is there, but we do not really have the respective labels. So learning this function, this mapping from X to Y, is typically not possible. Therefore, we have to rely on other things, and we can try to find out patterns within the data. We can try to do some dimensionality reduction on top of this data, but that's it. And then, of course, we come to reinforcement learning, which, as we will see in a bit, is fairly different compared to these two learning paradigms. And if I had to summarize it, the goal is to not learn from labeled or unlabeled data, but the goal is to learn from experience. Now, you might wonder, why is reinforcement learning so interesting, if you're wondering this, and why is it different from other forms of machine learning? Well, something that I've always found really interesting about reinforcement learning is the fact that, contrary to supervised and unsupervised learning, we are finally dealing with a learning problem which is very dynamic. So when it comes to supervised and unsupervised learning, we usually consider a learning framework which we know to be static. What do I mean by that? Well, essentially, what happens is that between the learner and the data that we're trying to learn from, there is no interaction whatsoever happening. So this is independent from whether the dataset we are dealing with is labeled or not. But overall, in supervised and unsupervised learning, between the algorithm, the model, the neural network, call it however you want, and the source that is used in order to train our model, there's no interaction happening whatsoever. So earlier I briefly mentioned supervised learning and this example of having a data set and the goal of classifying cats and dogs from it. Well, when we are dealing with a supervised learning problem, the learner, the machine learning algorithm, gets provided with this data set. This data set never changes over time, and the task also never changes over time. And that's about it. Then learning this mapping function from X to Y that I mentioned earlier becomes what we call a stationary problem, because basically the information that is needed for learning this function stays constant throughout the entire learning process. And something similar can be said for unsupervised learning as well. Even if our learning objective changes, we have still seen that we are dealing with a data set we can learn from, and again, this data set throughout training, throughout learning, does not change. However, in reinforcement learning, things become a little bit more challenging. The learner, or the agent that we are trying to train, acts in an environment which is very dynamic. So we will see in a little bit that we constantly have to deal through time with different information that changes, and this makes learning a non-stationary problem and therefore more challenging, but also, to my eyes, more interesting. There is, however, a similarity between unsupervised learning and reinforcement learning, which is the following. In both learning scenarios, we consider a scenario where there is no knowledgeable supervisor. And this is different from supervised learning, where somebody for us created a data set and labeled this data set for us in order to have all these X to Y pairs that we can learn from. Now, I've mentioned earlier that in unsupervised learning, we do not have this Y label whatsoever, and something similar happens in reinforcement learning as well. There is nobody which tells our agent what is good or bad, essentially, or that gives our reinforcement learning agent a bunch of examples that can be used in order to learn how to interact with an environment. We do not have any examples, previous examples, the agent can learn from. There is, however, some feedback which is provided to the agent, which is what we call the reward signal. In a bit I will give a more formal definition about this, and I will also show you where this comes from. but try to remember that indeed it's not really true that we do not have any supervision whatsoever, but there is indeed some feedback coming from the environment that can be used from the learner, from the artificial agent, to learn, and therefore possibly try to learn how to interact with the environment and improve over time, over and over again. If I would have to summarize the goal of reinforcement learning, and I think I have already mentioned this, I would summarize it as follows. The goal of reinforcement learning is to train an agent to interact with an environment. Now, how can this look like? There's many ways one can define an agent, and many ways one can define an environment, and also many ways of defining what it means to interact with an environment successfully. This is something I would encourage you to think about yourself, especially at the end of this lecture. But for now, I will provide some examples which might look appealing and that I think really explain a little bit what the goal of reinforcement learning truly is. What we are seeing here in this GIF is a classic reinforcement learning task that the reinforcement learning literature has been using for a very long time. Here what we see is an agent which is depicted by the blue square, which has to learn how to navigate this maze, and the main goal is that of reaching the bottom right part of this maze, which is depicted in green. Now, when it's interacting with this maze, we see that some squares are depicted in gray and some of them are colored in red. It means that basically the agent has only access to the gray ones and it cannot go through the red ones. These ones can be seen as walls, basically. The example that I'm showing here is an example of an agent which has already learned what we call the optimal policy, or it has learned the behavior, the optimal behavior when it comes to its interaction with the environment. We see that indeed it's able, from the starting position, which actually never changes, it's able to reach the final end square at the bottom right in the bottom right corner of the square. You can also see that this is an environment which is discrete. This basically means that the agent can choose between 4 different actions at every time step, and these actions, they correspond to making a move, so moving within the grid with respect to all the 4 possible cardinal directions. This means that the agent can go up, right, left or right, and this is enough in order to reach the end goal in the bottom corner of the square. This is another example which is a little bit more complicated and that the community started to adopt in between 2013 and 2015. In this case, the agent interacts with an environment which comes in the form of a video game. Specifically, these are video games from the 70s, and some of you maybe might recognize them. These are called Atari games, so something that probably our parents were playing with. We're I guess too young to remember them, but they became a very popular benchmark, adopted not really by the reinforcement learning community but by the deep reinforcement learning community. But I will show you later the differences between these two approaches, and here the goal is to play these games successfully. And actually, starting from 2015, we've had a lot of papers in the community that show that this is actually possible to do, and even to have artificial agents, computer programs that are able to play these games at a much better level than the human world champions of the Atari benchmark. So indeed, it's possible to have a world champion of these Atari games, and now these days it's possible to have an AI which is much better than these world champions. Another classic benchmark that is used not only in reinforcement learning but by the AI community in general is the game of chess. In this case, the agent we are trying to control is a white agent, and we're providing the agent with a position which should result in checkmate. And of course, now the goal of the reinforcement learning agent is that of finding the sequence that yields the checkmate on the board. Now, what's interesting, and if you know how to play chess, you will notice that the sequence that is found by the reinforcement learning agent is not really the optimal one. So what's happening here is that the agent decides to sacrifice his rook on c8. It gets taken back by the black's rook. Then he sacrifices the rook back, which gets taken by the black queen. And finally, checkmate is delivered by the white queen, moving from the c3 square to the c8 square. This is what's happening right now. But if you take a look carefully at the board, there's a much faster checkmate that white could perform, which corresponds to moving the queen from c3 to h8 alongside the black diagonal. That would be checkmate 2. Probably less spectacular because it only involves one move and not 3 moves. But yeah, this is a case where the reinforcement learning agent successfully managed to succeed at its task, but not in the most efficient way. But however, all these examples that I'm showing you are examples of agents interacting with an environment. And this environment can come in different forms: the grid world, the video games, or the chessboard. And also the goal that the agent has when it's interacting with this environment changes. It can change from having to reach the bottom square of the grid world to delivering checkmate and playing those video games. We have seen different examples of environments, and I will now have to introduce a little bit of mathematics, which allows us to define how these environments, reinforcement learning environments, can be formalized in a mathematical way. Therefore, I will introduce the concept of a Markov decision process, which is essentially the mathematical framework that we use for solving reinforcement learning tasks. If you're scared of the mathematics, don't be, because you will see that whatever weird symbols or formulas I will be using can be easily related to the examples I have mentioned so far, and I hope that the examples that I mentioned so far were enough for you in order to build some intuition about what it means for a reinforcement learning agent to interact with an environment, therefore with a Markov decision process. So again, MDPs are the mathematical framework that we use for solving reinforcement learning or sequential decision-making problems, and they consist of the following tuple. So we have 5 elements in an MDP formulation. We start with this calligraphic S, which corresponds to the state space. So basically, these are all the possible states that the agent can see, can interact with while it's learning. And based on the example that I've shown you earlier, these, for example, can correspond to all the possible configurations of a chessboard. Then we also similarly have A, which corresponds to the action space, and this corresponds basically to all the possible actions that are available to the agent. Again, this is something that I mentioned already actually. On the grid world example, the action space was 4 because the agent was allowed to move in 4 cardinal directions. Then we have 2 important functions. One is called the transition function, P, and this transition function basically defines the probability for an agent to enter into the next state, assuming it's in a certain state and it takes a certain action. A lot of environments are deterministic. This means that, for example, in chess, if you make a move, then you can easily predict how the board is going to look like once you have made this move, because this is part of the rules of chess. So if I decide to castle, or I decide to move my pawn at the beginning from one of the starting squares and move it by 2 squares, I know exactly how the board is going to look like once I have made this move. But some environments in reinforcement learning are stochastic, which means you cannot really predict this transition between one state and another state. Next to the transition function, we also have the reward function, which is a function that returns this positive or negative feedback, but this reward signal RT that I have mentioned earlier, and this is all the information that the agent actually needs in order to learn how to interact with the environment. Sometimes the reward can be obtained very fast. This is an example of those video games that I've shown you earlier. So it doesn't take the agent a lot of interaction with the environment before receiving some reward feedback, but sometimes this reward feedback can also be very, very sparse. This means that the agent has to wait for a lot of time steps before it knows whether it has done something well or wrong. And a typical example of this is the chess game, where you know that you've won the game only at the very, very end of the game, probably meaning that you have to wait 30, 40 or 50 moves before knowing that indeed you managed to beat your opponent. And then in this mathematical formulation of an MDP, we also add what is called the discount factor, which is a constant that is used in order to assign a different weight to different reward values. I will get back to this in a little bit. I will now also introduce the concept of policy. We actually have already seen it. I have referred to it as the behavior of the agent earlier, but technically in reinforcement learning we don't really refer to the behavior of the agent but to the policy of the agent. And basically this policy is what governs the interaction between the agent and the environment, and mathematically this we can see as a probability distribution over the action and state spaces. We have now reached a point that allows us to define what we call the reinforcement learning loop, or the agent-environment interaction loop. So if we have to summarize how a reinforcement learning agent interacts with the environment, we can do it as following. So you have to remember, and this is something that I've mentioned at the beginning of the talk, that we are dealing in a dynamic environment. So we're keeping track of whatever happens at each time step in time. And so what happens is that at each time step t, the environment provides the agent with a certain state. So this is basically what you would see when you are interacting with the environment. And this is the information that is needed for the agent to perform an action at a certain time step. Now, this action has some consequences. And the first consequence is that the environment will return a reward signal which is associated to the action that the agent has just performed. In sparse reward environments, this unfortunately means that the reward signal is 0 for most of the times. But if we're lucky, we get some feedback immediately. Because actions have consequences, the state of the environment will change. Therefore, we will move from state st to state t plus 1. And we can keep doing this and repeat this interaction possibly forever, meaning that at each time step the agent is in a certain state, performs an action, observes a reward, moves to the next state. But most of the times we deal with finite horizon problems, meaning that eventually the agent and environment interaction stops. This means that we will reach a state, st plus 1, which we call an absorbing state. Basically a state that does not have any successor state anymore. Therefore the interaction between the agent and the environment stops. And this corresponds to the terminal state that earlier we've seen to be the checkmate position, or reaching the bottom right corner of the maze. All these components, we can keep track of them and collect what we call a reinforcement learning trajectory. So a certain state, action, reward, and next state tuple correspond to what we call a trajectory tau in reinforcement learning. Most of the times these trajectories are enough for us to learn. And then if we stack a lot of these trajectories, one after the other, we are able to define what we call a reinforcement learning episode, which comes of length t, where t is a random variable that indeed represents how long an episode lasts. A key property of the reinforcement learning environment is that it is Markovian, meaning that it satisfies that it has two properties, and the first one is that the probability of visiting the next state is only conditioned on the current state and the current action that the agent has taken. So we've seen that we can gather a lot of trajectories while interacting with the environment, but the probability of entering the next state only depends from the current state the agent is in and the current action the agent is taken. In some way, the past in reinforcement learning does not really matter that much. The only information that is useful in order to predict the dynamics of the environment, therefore the probability of visiting the next state, are whatever is happening at the present time step. Therefore, whatever the agent is seeing at time step t, therefore the current state and the current action. Referring to an environment which is Markovian also means to define that the probability of observing a certain reward signal is also just conditioned on the current state and the current action. Similarly to before, it doesn't really matter which states and actions we have seen and performed in the past with respect to the reward that we are going to obtain. The reward only depends from our last action and last state we've been in. These are two very important properties that play a key role when it comes to the development of reinforcement learning algorithms. So, what is the general goal of a reinforcement learning agent? We can say that the goal is that of maximizing the total amount of reward it receives while interacting with the environment. And in the simple case, we define this as the return, and this comes with a mathematical definition of GT. But this is a very easy sum, so in time, basically, we want just to get as much reward as possible. However, when it comes to reinforcement learning, we do not really want to maximize this form of the return, but we would like to maximize what we call the discounted return. And what's happening here is that this gamma value, this discount factor that I have introduced earlier with the Markov decision process, starts to finally play a role. So what's happening here is that each reward signal that will occur in time will have a different weight. We will be multiplying this by gamma to the power of how many time steps in the future we are observing a certain reward signal. Now, this is really important because it allows us to do a few things. One important mathematical thing I will not dive into, but you will know about it after this talk, is that by including this gamma value into the sum, we will be able to deal with infinite horizon cases. And another thing which is also really important is that we can assign a different weight or importance weight to the different reward signals that the agent observes. You can see, for example, what happens if we are setting gamma to 0 in this sum. It means that if we try to train our agent to maximize this quantity g, all the reward signals it has observed after the current time step, they will disappear because we will be multiplying rt plus 1, rt plus 2, rt plus 3 by 0. Therefore, the only reward signal that will be taken into account will be the first one. This is something that usually we do not really would like to do because we would like to have an agent which is far-sighted instead of short-sighted most of the times. And one way to do it is to include indeed gamma into the sum and possibly set gamma to a high value. So this is an image which indeed shows that we do want to assign a discount factor to all the different reward signals that the agent will see while it's interacting with the environment, that in this case come in the form of these green diamonds. But something that you have to remember is that it's true that we are finally taking into account all of these reward signals, but their value will change a little bit based on how far or how distant in the future these reward signals are obtained. So in this case, we deal with a case where the reward signal has a value of 1 in the at the first time step it gets observed, but you see that this diamond changes a little bit over time, because indeed we are multiplying it by this gamma constant that then gets squared with respect to how many time steps in the future the agent had to wait before obtaining this reward value. So informally, we can define the ultimate goal of reinforcement learning, that of finding a policy that gets a lot of reward, possibly in the long run. And how do we formalize this long run mathematically? Thanks to this discount factor gamma. Now, how can we do this? There's 3 different approaches one can use in order to find this policy. The first one is based on value-based approaches. The second one is based on policy-based approaches. And the third one is based on model-based approaches. Let's start with the first one. So the goal of value-based learning or value-based reinforcement learning is to design algorithms which are able to model how desirable it is for an agent to be in a certain state, or how desirable it is for an agent to take a certain action in a certain state. I hope that this makes sense intuitively. If it does, we now need 2 more formulas which allow us to define this desirability mathematically. And how can we do this? We can do this by introducing a core concept in reinforcement learning, which comes with the name of value functions. The desirability of being in a certain state is typically expressed by what we call the state value function. The state value function, in this state value function, you might recognize something which is what appears between the squared brackets here. What appears here is nothing else than the sum of discounted rewards that I have introduced earlier. And we see that this value appears inside this expectation. What does this mean? Basically, it means that once an agent is in a certain state, thanks to the policy pi it is following, we would like to know how good it is for that agent to be in that specific state. And how do we know if a state is good or bad? Well, we can know this thanks to the notion of discounted return that I have mentioned earlier. Probably a state which is good is a state which will yield a lot of discounted rewards in the future. And this is what this expectation means. So the agent is following its policy pi, it sees a certain state, and we want to know how good this certain state is. Well, if the expectation of being in this state corresponds to getting a lot of discounted reward signals in the future, probably this is a very good state. And it's very desirable for an agent to be in this state. We can also do something very similar and model the same quantity and therefore the same value function, but by conditioning it on something extra. The previous value function was only conditioned on the state that the agent was in. But what we can do is we can also condition this value function on the state action combination. And this now becomes really, really powerful. Because what is this telling us? Well, it's telling us how good it is for a certain agent that is following policy pi to be in a certain state and take a certain action. And what is a good action? Well, it's probably an action that yields a lot of discounted rewards in the future. So how can we intuitively visualize these two value functions? You can imagine playing a game of chess. And what's the value function, the first value function, the state value function telling you? You're playing the game, you take a look at the board, and you feed this board position as input into this value function. This value function will tell you, for example, that the probability for you to win the game is 100%. So you're sure it's really good to be in that chessboard position at the current time step. Now, is this enough for you? Probably not, because when you're playing a game of chess, you do not only want to know that the chess position you're facing is completely winning, but you would also like to know what type of move you would like to make in order to keep your winning chances. And now this is exactly what the state action value function or Q function does. It's telling you, yes, this board position is completely winning, and it's completely winning if you make this move into the future. You might already guess that the Q function, or the state action value function, Q, is much more powerful than the state value function V. There's actually cases where it is enough to learn the state value function V, but I will not mention them today. But yeah, we typically rely on learning the Q function. And why is this the case? Because the optimal policy, it's very easy for the agent to derive an optimal behavior from the Q function. Because what's happening is that we will have a numerical value associated for every action that we can take in every state. Again, in the chessboard, the position of the board will stay the same, and then we will have a value associated to making every move that is available to the agent. And of course, because this value function models the expected discounted return that we will get into the future, and we want to maximize, basically we want to maximize the chances of winning the game, we do know which action we should take. We should simply take the action which has the highest Q value. This is a cute example that summarizes what value-based approaches do. Here we have our reinforcement learning agent, the robot, which has to learn how to or how not to interact with this slot machine. So this is the state that he sees, the slot machine, and the action that the agent can choose from is whether to pull the lever or not. And possibly it might win $2 or $0. Now the expectation that the agent has is that it's going to win $2, and probably this means that it has chosen to pull the lever of the slot machine, but we can see from the face of the robot that he is disappointed because indeed the slot machine did not return the expected reward that the agent had in mind. Of course, reinforcement learning is all about learning correctly these expectations and knowing that in a certain moment in time it's actually worth it to pull the lever of the slot machine, whereas many other times probably it doesn't make too much sense because these machines, they're made in order to screw you. Okay, this is about it for the value-based approaches. We will now see policy-based approaches. The goal of policy-based methods is that of learning directly a policy by without having to rely on any of those value functions that I've shown you earlier. This has several benefits because this allows us to learn policies that aren't deterministic, therefore they are stochastic, and that are also suitable for continuous action spaces. These are two big limitations of value-based approaches. Value-based approaches will only give you a policy which is deterministic. The optimal policy will never change over time, but sometimes the optimal policy might involve some randomness. Therefore, we cannot use the value-based approaches that I have mentioned earlier. And also the value-based approaches that I've mentioned earlier, they cannot be used when the action space is continuous. How do these policy-based approaches work intuitively? Here again, we have a robot which is trying to find out what's the best policy, the best map here that will allow him to, I don't know what his task is, probably he has to escape. And therefore, what he's trying to do is he's trying to find the best possible map among a bunch of maps that are contained in this box. And policy-based approaches do exactly that. You see that now we are not really reasoning in terms of expectations and how desirable it is to be in a certain state and perform a certain action. These methods here, they directly seek for the best possible behavior among a set of behaviors. We then also have model-based approaches, and the goal of this family of algorithms is very different compared to the one of value-based approaches and policy-based approaches, which also come with the name of model-free reinforcement learning. I'll give you a brief reminder about the MDP formulation that I have introduced at the beginning of this talk. I've said that the goal, we've seen that parts of the components that define a Markov decision process are these two functions: the transition function, which defines the probability of entering the next state given a current state and action, and the reward function, which is the function that returns the reward signal to the agent. P and R are also known and defined in the reinforcement learning community as the model of the environment. And why is this the model of the environment? Because they really are able to express how the environment works. So we can summarize the dynamics of the environment thanks to these functions. When it comes to value-based approaches and policy-based approaches, the agent does not really care about this transition and the reward functions. In the usual reinforcement learning setting, these functions are unknown, so there's not much we can do about this, and therefore we have to rely on learning something else. And this something else can be the value function or the policy, but we can also try to learn these functions, the transition and the reward functions. Interestingly, this corresponds to solving a supervised learning problem, and if you're able to do this, learning the transition function and learning the reward function, it becomes also an easy task to interact with the environment, because you know exactly, given a certain state and given a certain action, which next state you will encounter, and also which reward signal will be associated to the next state. If you can do this, you can, for example, construct a tree which explores all the possibilities that that the agent can face once it is in a certain state and action. You can easily predict the next state and the reward signal that is associated to the next state. Therefore, you know that your optimal policy will be the one of exploring the nodes in the tree which correspond to the states that have the highest reward signal associated to them. The reinforcement learning literature seems to agree that model-based approaches are more sample efficient than model-free reinforcement learning approaches, meaning that you need way less trajectories to learn the transition function and the reward function compared to the number of trajectories you need if the goal for you is that of learning the value function or the policy. And this is our favorite robot again, who's trying to learn how the environment works. He has this other robot on the side, and he's trying to model the dynamics of it. Now we have seen that the agent has to interact with the environment based on its policy pi. I would like now to mention a crucial dilemma that every reinforcement learner faces, which is called the exploration-exploitation dilemma. So we know that once the agent interacts with the environment, it will have to choose between two options. It will have to rely on whatever it has learned from the environment, or it will have to decide that whatever it has learned from the environment is not enough, and therefore it has to keep interacting with it with the goal of improving the current knowledge of it. Does it mean probably our expectations in terms of value functions are not accurate, the policy that we have learned is still far from the optimal one, or the model that we have constructed of the environment does not really reflect the true dynamics of the reinforcement learning task we're trying to solve? And this is a big dilemma because we never really know when to move between the exploration or the exploitation phase in reinforcement learning. Here we have our favorite robot again, who's facing the similar dilemma. He has to decide whether it has to have dinner at the usual place, which he knows to be good, or it probably also could go to this very new restaurant, which might be much better than the usual place, but also much worse. This is not an easy task, as the agent, the reinforcement learning algorithm, must decide when to explore and when to exploit. There's many ways, there's a lot of literature which reviews different exploration-exploitation strategies. Here I just put you the formula for one of the most popular ones, which is called eGreedy. And here the idea is very simple. This is defined for value-based approaches. As you can see, this Q function appears again. Here the idea is that at the beginning of training, we want an agent which explores a lot, and by the end of training, we would like an agent which barely explores, because we hope that it has interacted with the environment that much that it has learned what the best restaurant in town is. I will now approach the second part of my talk, which is about the field of deep reinforcement learning, which is an emerging field of artificial intelligence that combines neural networks, therefore deep learning, and reinforcement learning to create agents that are able to learn via trial and error. Deep learning and reinforcement learning is a successful combination because it allows us to train agents that can act when the environment has a continuous state action space, that are also able to generalize across different environments, and can overcome some severe computational memory limitations that characterize classical reinforcement learning, which we also call tabular reinforcement learning. And deep reinforcement learning over the last decade has been able to tackle a lot of challenges and tasks that were considered to be impossible to the community. One of these was the game of chess or the game of Go. I would like to show you first what happens when we are dealing with a continuous state space and why deep reinforcement learning can be useful in this scenario. This is one of the video games I have mentioned at the beginning of the talk. This is what we call the game of Pong. The goal here of the agent is to control this pedal on the right, and you can move this pedal to the right, the left, or you can also not control it, which means that the position of this pedal will not change in time. And the goal is that you're playing against your opponent, which is also controlling this pedal, and you're trying to bounce the ball back and forth. And ideally you would like to have the ball bounce in your opponent's territory without it being able to catch the ball with its pedal. Now, this Atari game, the state space, it's continuous because we are dealing with a high-dimensional image. This means that most of the tabular reinforcement learning approaches cannot really be used. There's something else which is interesting here, that in order to play this game successfully, a lot of the pixels that are contained within the image are not really informative at all. This is what I'm showing you at the bottom of this image here. I'm plotting what are called saliency maps, so these heat maps on top of the pixels that the agent thinks are informative in order to play the game successfully. And you can see that actually out of 255 pixels in each of these states, only a very specific subset of pixels is informative in order to play the game correctly. Most of the times these pixels, they correspond to informative parts of the image, like for example the position of the ball, the position of the pedal that the agent is controlling, and also the scoreboard, which apparently gives the agent enough information. You can also see that all the states of the game look very similar among each other, and again that small portions of the state space are actually informative. Sometimes you can do some pre-processing, meaning that the original state space can be reduced, but researchers know that you can only do this up until a certain point, and despite the pre-processing operations that the computer vision community usually adopts, the state space remains highly dimensional. Another example of how quickly the state space can grow is given by the popular board game Go. The game of Go has two very simple rules. It is played on a board size of 19 times 19, and on each location on the board you cannot place a stone, which can be white or black. And the state space, therefore, if you do the mathematics, corresponds to this huge number, 3 to the power of 361 states. Now you can imagine that if your goal, instead of modeling how desirable it is for an agent to be in all of these states, with the value-based approach, as I have mentioned earlier, that we will have some significant limitations. There's no computer which can store all this information in it. And you can easily see that things become even worse when it comes to modeling, for example, the state action value function Q, because there we do not only want to model how desirable every board position is, but how desirable it is to actually place or not place a stone. And therefore this number here increases even further. Fortunately, we can use deep reinforcement learning to overcome many of the limitations that I have just mentioned, thanks to the use of neural networks. These neural networks, they have some important properties. Among, I will mention 3 of them. Probably the most important one is that neural networks are universal function approximators. This means that they can technically learn any mathematical function, just like all the functions I have mentioned earlier. They can be learned by a neural network, and they can also be learned in not such an exact way. And for many tasks, this is enough. So we do not really care about learning the exact value function for every possible board position of the game of chess, because many board positions, they are similar among each other. Therefore, it doesn't make sense to learn the exact value for all these different combinations. Neural networks, especially convolutional neural networks, are also very powerful feature extractors. Going back to the game of Pong that I shown you earlier, they're able to automatically identify which pixels are relevant in the state space for us. Actually, those examples that I've shown you come indeed from a convolutional neural network that automatically figure out that the only pixels that were necessary in order to play the game, the video game of Pong, correctly were the ones surrounding the pedal and the ball, which was getting bounced back and forth. And interestingly, neural networks, they can be trained end-to-end, which means that you can provide these neural networks with high-dimensional inputs, and they can be trained in order to learn either the value functions that I mentioned earlier, they can be trained to learn a policy, or they can be trained in order to to learn the dynamics, the model of the reinforcement learning environment. Over the last decade, there's been many successful examples that showed us that it is indeed possible to have this successful marriage between deep learning and reinforcement learning. The probably most famous example with which everything started is indeed related to these Atari games that I've mentioned earlier. It was the very first time a computer system was able to learn by trial and error how to play those games by just receiving as input raw information about the state space, basically just the screen that was recorded from the Atari emulator. Then, thanks to a neural architecture that was trained in a value-based fashion, this algorithm, which comes with the name of Deep Q network, was able to beat the best players on Earth on the Atari benchmark. There's also an excellent YouTube documentary about AlphaGo, this system modeled by the Google DeepMind that managed to defeat the world champion of Go. I think this was 2017. This was a system which was indeed trained in with deep reinforcement learning techniques. And these days, I'm happy also to see that there's some more practical applications of deep reinforcement learning. Few of these are the following. DeepRL is currently being used in order to govern the path of stratospheric balloons, which I always found really nice. And they also use it at CERN, they have some very complicated machinery over there, which contains plasma and nuclear fusion, and this whole machinery is controlled via a deep reinforcement learning system. Now, this is the end of my talk. I hope you have enjoyed this journey with me in the world of reinforcement learning, and I will like to thank you for your attention, and I will see you soon. Thanks.